In this video, we're going to explore the DC bias derating effects of multi-layer ceramic capacitors, what that means, why it's important and why it's something you need to consider for your own designs, and finally I'll show you how to measure the DC bias derating effects using a Bode 100 vector network analyzer as well as some customized test setup to see how manufacturers typically also will require this type of data. Considering DC bias derating in your designs is incredibly important. It's something you should be doing and probably need to do in pretty much every design you consider. It's important for filters, power supplies, and much, much more. And I hope this video sheds a bit of light on that. A huge thank you to JLCPCB for sponsoring this video. The PCBs we're using in this video and in future videos were manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB provides easy, affordable and reliable PCB and PCBA services. The web interface is super easy to use, as well as their PCB and PCBA prices are absolutely incredible. For instance here, a 10 by 10 centimeter 6-layer PCB VN pad with Enix surface finish is only $35 for 5 pieces, and their assembly is similarly affordable as well. I've also found JLCPCB to be super reliable with a high quality, and I can get my PCBs back in about 1 or 2 weeks, which is absolutely incredible and allows me to work at a much faster and better rate. Make sure also at the time of making this video, you can get $30 off with a coupon for JLCPCB's 6-layer PCB services, which includes Enix surface finish and no engineering fees for VN pad, which I think is pretty incredible. Links will be in the description box below as usual. A huge thank you also to Altium for sponsoring this video. If you'd like to give the powerful Altium 365 platform a try, make sure to follow the link in the description box below or go to altium365.com/yt/philslab and you can get yourself an Altium 365 free trial. Altium 365 brings many impressive features to Altium Designer, such as collaborative design reviews, mechanical co-design with SolidWorks, Fusion and more, manufacturing collaboration, ease of BOM management, and much, much more. If you'd like to check out in part some of the cool features of Altium 365, you can also go to my GitHub profile and my GitHub IO page, pms67.github.io, and check out some of the example hardware designs that were shown on the YouTube channel here. With the Altium 365 viewer, you can explore the boards in your own time and in real time. You can look at the 3D models and you can scan through the PCB layers as well as the schematics on some of the designs as well. I'll leave links in the description box as usual. Before we actually look at the DC bias derating effects and also perform measurements on DC bias derating on real-world capacitors, let's briefly run through the multi-layer ceramic capacitor basics just to make sure we're familiar. I'm condensing this information quite a bit, but do check out video number 114 on my channel, which goes through multi-layer ceramic capacitors in far more detail. The link will be in the description box below. MLCCs are multi-layer ceramic capacitors. These are surface mount SMD type capacitors available in various standardized sizes. As pictured on the right hand side, I've pictured some typical imperial sized capacitors, and in this video I'll also typically refer to them in their imperial size. MLCCs are typically given with a nominal capacitance, that might be 1 microfarad, plus minus some sort of tolerance, 10-20%, a certain dielectric type, as well as a voltage rating. For instance, voltage rating meaning the maximum absolute voltage a capacitor can withstand before breaking down. For example, you couldn't use a 10-volt rated capacitor at the output of a 24-volt buck converter. Overall, there are 4 main classes for multi-layer ceramic capacitors, but we'll only be focusing on 1 or 2 common classes. Class 1 have the highest capacitance stability as well as highest accuracy. These are typically COG type or NPO type capacitors. They, however, don't have particularly large values of capacitance, so typically maybe around up to 100 nanofarads or below. Class 2 ceramic capacitors are very, very common. They offer a much higher capacitance versus package size, so you could go up to 100 microfarads depending on the package size, but that comes with a trade-off that these larger capacitances for small packages typically offer lower stability, and we'll see what stability means, as well as accuracy. What type of capacitor, if it's MLCCs or if it's other types such as tantalum or aluminium electrolytic, what voltage ratings, what dielectrics, what tolerances, and so on need to be chosen very, very carefully depending on the situation. Some examples might be what, in a particularly hot environment for IC power decoupling, what do you choose? What nominal capacitance, what dielectric, and so on. This might be different to what you use on a USB-C PD power line filter capacitor, where PD voltages can go from 5 to 20 volts. A completely different situation might be an AC coupling capacitor in audio path. You might not want to use class 2 multi-layer ceramic capacitors there, and so on. So capacitor choice is a huge topic on its own. Please do check out video number 114 for more details. focusing particularly on class 2 multi-layer ceramic capacitors, because in this video we are trying to measure particular DC bias effects. This slide was taken from the previous video number 114 on multi-layer ceramic capacitors. A large issue these class 2 multi-layer ceramic capacitors have is variations in their nominal capacitance. So again, they might be stated at 1 microfarad or 10 microfarads plus minus some tolerance, but that capacitance is only the capacitance without any DC bias, no DC voltage across it, and at a specific temperature and aging. I've taken two graphs from manufacturers and plotted them on the bottom right-hand side of this slide. The first graph has DC voltage on the x-axis and the capacitance change in percent on the y-axis. At the 0 point on DC voltage, with no DC voltage applied, we can see the nominal capacitance change is 0%. So for 1 microfarad capacitor, we are still at 1 microfarad. However, this seems to be a 16-volt rated capacitor. As we move up the chart to, let's say, 10 volts applied across this capacitor, we already drop more than 50% in capacitance. So our 1 microfarad capacitor now drops down to a 500 nanofarad capacitor or even less. So that means the rated voltage of the capacitor has, for this class of capacitor, not very much to do with the actual capacitance. It is just the absolute maximum voltage we can apply to this capacitor. But we have to be very much aware of that any voltage applied across the capacitor, if that's DC or AC, for this particular class of MLCC capacitors, means a reduction in the overall capacitance. We have similar effects if we look at the AC voltage versus capacitance change, as well as temperature, which I'm showing on the right-hand side as well as aging effects. In this video, I'd like to explore the DC bias effects more and actually perform measurements and see how you could perform these measurements yourself or how manufacturers will typically do this. There are, of course, issues with this derating. First of all, we have a reduced capacitance, so the value of capacitance we actually have is not what we might expect. Additionally, the capacitance depends on external parameters which introduce nonlinearities into particular circuits. For instance, for filters, we have this RC filter shown on the right-hand side with a series resistor and a capacitor, which forms a low-pass filter with a nominally 100 nanofarad capacitor. With a high enough voltage applied across C78, this capacitor, that will reduce the capacitance and therefore it will shift the cutoff frequency. Also, if we apply a large amplitude AC signal at the input of this filter, that will of course also appear in a somewhat attenuated state across C78, meaning with that change in amplitude due to our time-varying signal, that will of course also change the capacitance, and that might introduce nonlinearities. You will get other effects other than the simple linear model you had before. Another area where derating can cause issues is, of course, power supplies. So I've shown a typical buck converter here with input and output capacitors. Now, any voltage across the input or output capacitors will, of course, reduce their nominal capacitance, again, depending on the type of capacitor you choose. And a reduction in that capacitance will change the stability because that affects the loop gains, the bandwidths, and the overall control system of this feedback-controlled buck regulator, which in turn might affect the response. It might affect the output ripple performance, overshoot, undershoot, and much, much more. These are just two examples, but there are many, many more. Reduction in capacitance typically means a change in the self-resonant frequency. We will get a higher impedance. If we're using them for bypassing or decoupling, our capacitors become less effective. We get nonlinearities introduced and more. So derating really needs to be taken into account in pretty much any design. Before we move on to measurement, there are of course techniques to mitigate or to counteract this derating. The first is simple. You could just simply choose a larger nominal capacitance. So if you know your capacitor is going to derate because you're applying a certain voltage across it, let's say it derates by 50%, you could just double your capacitance from 1 microfarad to 2 microfarad, and then with that DC voltage applied, it drops down to 1 microfarad, which is what you wanted to start with. You can either choose a larger nominal capacitance capacitor, or of course you can parallel capacitors, as I'm showing in the top right image for this output of the buck converter. Another option might be to choose a higher voltage rating of your capacitor. Now, this doesn't always mean you will get less derating. You always have to check the manufacturer spec sheets, but a rule of thumb is to choose your capacitor voltage rating at 2 times the maximum applied voltage. So if I'm using a capacitor which has a DC voltage of 3 volts across it, I might choose a 6 volt or 6.3 volt rated capacitor at an absolute minimum. The capacitor type and dielectric, of course, plays a huge part. As we saw, there are different types of MLCC classes. We also have the options of tantalum, aluminium electrolytics, film, and more. But of course, there are pros and cons to those other than just derating, specifically size, aging, and more. Package size is also an option to help aid derating in, very generally speaking, larger packages. So moving, let's say, from an 0402 capacitor to an 0805 or 1206 typically means these can withstand higher voltages, which may correlate that they actually derate less with a DC voltage applied across them. But again, check the manufacturer spec sheets. This is a rather large generalization. Importantly as well, capacitors aren't created equal. You always have to compare capacitors. If you're doing a part search on mouse or DigiKey or wherever, and you're finding 10 microfarad 0603 X5R 10% capacitors, these are not all the same. You do have to check out the DC bias derating charts and any derating charts that could come into play for your specific design. You cannot simply just choose a capacitor based on its nominal voltage, nominal capacitance, package size, dielectric, and tolerance. There's much more to this. Now we would like to actually measure the DC bias derating effects on multilayer ceramic capacitors. For this, I will be using a 2-port shunt-through measurement setup, and I won't be going into much detail here because I've already covered this in video number 151. Again, a link to this will be in the description box below. This video shows you the complete measurement setup using a Bode 100 vector network analyzer, a custom component tester, common mode chokes, and more, but this was for a pure AC-based measurement of capacitors and inductors. In this video, we want to apply DC bias, which can introduce problems with our measurements and our measurement instruments. I've drawn a block diagram here of our measurement setup, and if you compare this to video number 151, it's very, very similar, except we have an addition of 2 DC blocks, and one of them also being a bias injector. So from our Bode 100 vector network analyzer, we're using the output, which is an AC generated signal, and feeding that through a DC block, and we'll get to what a DC block actually looks like in just a second, and a bias injector. After this DC block and bias injector, we now have a DC offset in addition to our AC signal generated by the Bode 100 output. We feed that into the device under test, which means we can vary the DC voltage, we can vary the AC voltage, and we can check DC derating. Our device under test in this case will just be our capacitor in parallel for this 2-port shunt-through measurement. We feed that back through another DC block to remove the DC offset. Then we have the AC signal going through a common mode choke. And this is again mentioned in video number 151. This is to reduce the effect of ground loop errors, and that signal then feeds into the second input port of the Bode 100. We need to use DC blocks and bias injectors because typically we can't directly apply at least arbitrary large DC biases or voltages to most measurement instruments. For instance, the Bode 100 has a maximum voltage you can apply to its output of about 3.3 volts RMS because it has a 50 ohm series resistor to its output with a certain power rating. Similarly, for the inputs of the Bode 100, this is 7 volts RMS, again due to a 50 ohm resistive input setting for the 2-port shunt-through measurement. Therefore, we need a way to mitigate this, and that is actually quite a simple solution. You can think of it as somewhat like a bias T. We have a DC block and a bias injector. DC block effectively just means an AC coupled series capacitance, and I've drawn a simple schematic here. So we have our AC signal, then we have a blocking capacitor, and the bias injector is simply a resistor that pulls to a DC source or a bias supply. After the blocking capacitor and with this bias resistor, we now have a superimposed AC plus DC signal which can feed to our component under test. The bias resistor is typically something around 10 kilo ohms, and the blocking capacitor has to be chosen to be large enough given that we are running a 50 ohm based system and measuring low impedances that are low frequency cutoff frequency, mostly out of the measurement range. That typically means we need a large blocking capacitor due to the high-pass filtering effect, or, as you see here, this is the custom DC block I made and bias injector. We have lots of paralleled capacitors to give us a fairly large capacitance. I happen to have 40 10 microfarad capacitors in parallel and the 10K bias resistor. Again, issues with this are the DC block capacitance, what loads are we running with, and therefore what corner frequencies do we have, because this now acts as a high-pass filter. Also, the DC block capacitors here, because I need a fairly large capacitance. Another issue is that these DC block capacitors, because I need to have a fairly large capacitance, I need to use quite a lot of them. These need to be able to handle positive and negative voltages due to the AC signal. And the particular ones I'm using here are actually multilayer ceramic capacitors, so they will have their own nonlinearities, they will have their own derating, they will have their own maximum ratings. And this, of course, needs to be taken into account within the measurement. Ideally, you would then have to recalibrate the entire measurement setup. Again, check out the previous video number 151 on how that works for every single DC voltage applied, because if you apply a different bias voltage, that will change the capacitance of my DC block. For this video, we'll keep it fairly simple. I won't recalibrate for every DC voltage we apply because that would just take a bit too much time. From the previous video, we also saw this calibration and component test board which is very, very simple but designed specifically for the two-port shunt-through method. This is what I use to do my calibration, so for the open, short, and load, rather than a through calibration also for this video, and we can use this to also calibrate when we have the DC blocks in series with the device under test, as well as the common mode choke. So the setup for calibration is exactly the same as before in the previous video, except now I have these DC blocks in series before and after the device under test. After performing the calibration with this, then we can move over to the device under test. And for this case, in this video as well, we will be simply looking at 0603 type multi-layer ceramic capacitors and how we can measure the DC bias effect, again, using the two-port shunt-through measurement. For more accurate measurements, we would then need other test fixtures for 0805, 1210 components, or whatever capacitors we want to measure or devices we want to measure. But in this video, I just like to show you the very basics of how we perform these measurements. In terms of measurement setup, here are the real life pictures. So I've got my Bode 100 with the output and channel 2 input ports hooked up, and I'm using a Rigol DP831A programmable DC power supply to act as my DC bias source, so I can go anywhere from 0 to 30 volts. Of course, we can't go over the maximum rating of the particular capacitor we're measuring. From the Bode 100 output and from the output of this programmable DC power supply, I'm going into my DC block. So this is the AC signal coming from the Bode 100, as well as the positive and negative terminals of my power supply. This DC block just currently has a case around it. And then at the output port on the right-hand side, we have DC and AC signals, which then feeds into the two-port shunt-through test PCB with the open short load calibrations as performed in the previous video, and then finally hooked up to our device under test ports, so input and output ports connected with a 0603 type capacitor soldered on, and we'll see exactly what that is in just a second. From the output, we then feed into another DC block and bias injector, except now I'm not applying any DC bias to this 10K resistor, so it's floating. I could of course desolder it to make it a bit neater, but this is now just acting as a DC block but not a bias injector, to remove that DC offset before we feed it into the low frequency common mode choke, again to suppress ground loop errors, before we go back to the Bode 100 into the channel 2 input port. I'm now in the Bode Analyzer suite. I've selected the two-port shunt-through measurement method, and I've already performed the calibration as per the previous video on the two-port shunt-through measurement method, except in this video, of course, we're using two DC blocks. One of them we're also using as a bias injector. So this, of course, needs to be taken into account within the calibration, as well as any DC bias you apply, you should recalibrate for that specific DC bias, because of course your DC block is not ideal either, and its capacitance, if it's using multi-layer ceramic capacitors, will most likely change as well, and therefore its filter characteristics will change. In this video, we'll keep it a bit simpler. I won't be recalibrating for the sake of time. I've just done a 0 volt DC bias calibration, and here's the result after measuring then a 100 ohm resistor. You can see we're getting nominally 100 ohms. There are some minor excursions, and we're getting about 0 degrees of phase after the open short load calibration, again with the DC blocks as well as the common mode choke. In terms of measurement setup, my start frequency is 1 kHz. I set this deliberately a bit higher because this is still well within the measurement range, but it's above any potential DC biased cutoff frequency, high-pass filter effects of the DC blocks, so that's why I'm starting at 1 kHz, and I'm just going up arbitrarily to 40 MHz so we can still capture information on the self-resonant frequencies of these small multi-layer ceramic capacitors. My source level I've reduced down to something around -6 dBm. We don't want to make our source level too high that we overdrive our components and we risk introducing non-linearities and errors into the measurements. And of course, our multi-layer ceramic capacitors, these class 2 types, are also susceptible to AC derating, so that's why I'm keeping my source level fairly low, and I've set my attenuators appropriately to somewhat maximize my signal to noise ratio. So now let's move over to the component we're testing. The particular component is a 1 microfarad nominal capacitance 0603 capacitor with ±20% tolerance, X5R type, and 16 volts DC maximum rating. This is a part from Murata. This is a particular part number which I won't be reading out, but nicely enough, and that's why I like using Murata parts, is that they have pretty elaborate characteristic data for their parts. So we have an impedance versus frequency plot, we've got an ESR versus frequency plot. Importantly for us now, the capacitance change versus DC bias, capacitance change versus AC voltage, and temperature, and so on. So for this video, we are mostly interested in just the DC bias characteristics. So we'll be measuring a couple of points. We'll be measuring at 0 volts DC bias, at 4 volts DC bias, and 12 volts DC bias. And then we can compare our measurements to those of the manufacturer, which hopefully should serve as somewhat as a baseline truth. You saw the measurement set up previously. What I now have is a 0 volt DC bias on my capacitor, so my power supply is set to just 0 volts and will perform a single measurement of our capacitor, so completely unbiased. To do that, all I have to do is now click on single measurement and acquire our new impedance versus frequency curves. The top trace shows impedance magnitude versus frequency, and the bottom trace shows phase versus frequency. And here we can get our typical multi-layer ceramic capacitor plot. We have this downward facing slope, this capacitive region, until we hit the self-resonant frequency where the equivalent series inductance and the capacitance cancel each other out, and we're left with equivalent series resistance at that specific frequency and point, after which we go into this ESL-based region, the equivalent series inductance. What we're interested in is this lower part of the trace, so around a kilohertz. What is the capacitance there? And nicely enough, for the Bode 100, if we go to trace 2 or any trace, we can change the format from, let's say, phase to capacitance. And if we look at our cursor under trace 2, we can see our capacitance for a 0 volt DC bias is around this region, about 960, 970 nanofarads. Given our capacitor we're looking at, we have a 1 microfarad capacitor plus minus 20% tolerance, so that's anywhere from 0.8 or 800 nanofarads up to 1.2 microfarads. So our measurement is well within range, it seems. And this again is with 0 volts DC bias. Now, as we start increasing the DC bias, we can follow this curve of the DC bias characteristics. Let's go to 4 volts. We can see the capacitance change given by Murata is or should only be around minus 6.5%. Keep in mind they're also showing that this is measured at 25-degree ambient temperature and an AC voltage of 1 volt RMS. So if you want to get exactly these results, of course, you would have to match the ambient surroundings as well as the AC voltage applied across this. But for us, we will just be concerned with the DC bias for now to see if we're getting approximately the same ballpark values. So let me adjust my DC power supply now to 4 volts. And when I adjust it, I'm adjusting it slowly to not induce any spikes or transients that can pass through the DC blocking capacitors. Before we perform the measurement, let's go to measurement and store this current measurement in memory, and we'll call this something sensible like 1 microfarad 0 volts DC, so we can compare it to our next few measurements. With my power supply now at 4 volts DC, let's click on single measurement and see what happens. Again, we get a very similar characteristic curve, but it is slightly different. You can see the red trace is the new one, which has an overall higher impedance than our previously unbiased capacitor measurement. And this makes sense because with DC bias, we're getting a lower capacitance, which in turn means an overall higher impedance across frequency. Now the change is minimal because actually the capacitance change is minimal, but there is a change. Also, we can see due to the change in capacitance, we are getting now a higher self-resonant frequency. Our self-resonant frequency in radians per second is 1 over square root equivalent series inductance times capacitance approximately, which means for lower capacitance, we will have a higher self-resonant frequency, so that makes sense. The ESR, of course, is not changed, as well as the ESL isn't changed, so our inductive region is the same. So we can see our impedance overall is increased, and our self-resonant frequency is shifted higher with our DC derating. But now going back to the capacitive range, let's just drop our cursor somewhere around 2 kilohertz, and we can see we're getting now about 850 nanofarads of capacitance. Previously, we were somewhere around 950 nanofarads, so this is somewhat close to a 6-7% change, maybe a slight bit more derating for this particular part. So we're pretty close to what the manufacturer has measured. Of course, we have slightly different operating conditions as well. But now let's increase the DC bias quite a bit so we get a quite drastic change in capacitance. They measure at a DC bias of 12 volts, they're getting about a 50% capacitance change. So suddenly your 1 microfarad capacitor might only be a 500 nanofarad capacitor. So let's see if this holds true. So again, I'll save this trace to memory. We'll call this 1 microfarad at 4 volts DC. I've now adjusted my power supply again slowly to a 12 volt DC bias. Let's start a new single measurement and see what happens. And we can see straight away our impedance has jumped up quite a bit, again due to the derating because we now have an even lower capacitance, and our self-resonant frequency has also shifted higher, again because our capacitance has dropped and our equivalent series inductance stays the same, so therefore the self-resonant frequency must go up. If we go back into the capacitive region, we can see our capacitance, which started maybe around 950, around 1 microfarad, has dropped to 460 nanofarads, which is very close to the minus 50% change that Murata indicates on the DC bias characteristics. So quite a significant drop, even though this particular part is rated up to 16 volts. This is an 0603 package, so fairly small, but not terribly small. Above about 8-9 volts, this specific capacitor does lose quite a bit of capacitance, and this is something you really have to be aware of for the points mentioned previously. Now, of course, we could repeat this experiment measuring different types of capacitors, multi-layer ceramic capacitors, tantalum, comparing them to aluminium electrolytic, and so on. But we now understand the basic principle of how to do these measurements and what happens with a change in capacitance due to derating. What I would suggest when you're choosing parts is to scan through the manufacturer's provided data, because they have pretty accurate measurements typically. If you can't find these measurements, then of course you'll have to measure them your own if you would like to use that specific part for whatever reason. Thank you very much for watching this video. I hope it was useful, and I hope it gave you a basic insight into the derating of multi-layer ceramic capacitors, specifically with respect to DC bias. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest embedded systems, PCB design, test and measurement, and general electronics videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.